Okay. Otávio. Okay, so good afternoon. So let's start the last lecture of this introduction to large-scale structure. So Raul gave 3 lectures, and I'm getting off with only two, which is great. And this is a preparation for next week's lectures by Marko Simonovic. So he's going to continue with the large-scale structure discussions. So what I want to do today is to finish the discussion of the spherical collapse model and then use the spherical collapse model to try to describe, again, a very simple way, a very simplified model to describe the amount of dark matter halos in the universe. And finally, talk about something called the halo model, which is a non-perturbative model for the, that you can use to compute power spectrum or any endpoint correlation functions of the density perturbations. Okay? So yesterday went too slow, but I don't want to go fast, so I'm going to continue to be slow. So let's finish the spherical collapse model. So you remember that this is a model where you have an Einstein de Sitter universe with a spherical perturbation with uniform density inside this Einstein de Sitter universe. And given this assumption, the assumptions that the mass inside this perturbation is conserved, you can solve the model exactly. You can solve for the evolution of this perturbation exactly, given these assumptions. Einstein de Sitter, spherical perturbations, mass constant inside the perturbation. So what we discussed yesterday is that you can solve, so there's I call it a radius for this perturbation. So it's a circular perturbation, there's a radius. And the idea was to find the dynamics for this. And in an Einstein de Sitter universe. So we found this, you probably found also the solution, that you can write this in a parametric way in terms of a variable theta. And the solution is that the radius of this perturbation as a function of this variable theta goes like A 1 minus cos theta. And the time as a function of theta is like B theta minus sine theta. So it was an exercise, and A and B are given by omega matter inside the perturbation, not omega. So omega matter in the Einstein de Sitter is 1. So this omega matter inside the perturbation over 2 omega matter minus 1. And B equals 1 over H naught omega matter 2 omega matter minus 1 at 3/2. So who showed that this is the solution to the Friedmann's equation in the perturbation? Yeah, Meredith is very good, yes. Probably did on your head. Okay, so guys, you should, so there's only one person that did the exercise, okay? You should try to do this exercise. This is a school, you're supposed to do exercises. Okay, very good. So what that means is that I can plot this, the radius of the perturbation, r, as a function of theta, this variables for these solutions. And what happens is that if you start at a certain initial value, it goes to a maximum, decreases, and goes to 0. Okay, so this is the turnaround radius. And the turnaround radius, we call it turnaround. It happens at a theta equals pi. And you can compute what the value of the turnaround radius is. It's 2a, because it's r of theta equals pi. And that's 2 times a. And it occurs at a time which is b times pi. That's the turnaround. So this is turnaround. When the perturbation stops expanding and starts to collapse again. It's called turnaround radius. And then it collapses when θ equals 2 pi. And it collapses at the time, collapse time, which is given by 2b pi. So the great thing about this model, again, is that we can solve everything. And you can compute the perturbations. And you can compute the evolution. Of course, you can compute the perturbations. And what happens when, again, what happens to the perturbation with delta when it reaches this value here at 2b pi? It diverges, right? But you can also compute the linear perturbation. And the linear perturbation does not diverge. And so what happens is this. So I plot the perturbation delta. I can plot as a function of time if you want. Okay, so it goes linearly, and then at collapse time, this thing diverges. But you can compute the linear perturbation evolution of this of the linear evolution of this perturbation, and of course at small times it goes like in nonlinear. But then it detaches, never blows up because it's the linear. An important thing is that we can compute what is the value of the linear perturbation theory when the nonlinear collapses. And that's what we call this delta C, delta collapse. And that we can compute in this model, which is this 1.687, whatever. Okay, good. So that's how we did yesterday. So what I want to discuss here now is the following, that we know that there is no actual divergence in the real universe. What happens is that these structures that are being formed, somehow they thermalize, they virialize. Even in gravitational, even if they only have gravitational interactions, they can exchange angular momentum, their tidal effects, they end up virializing. So what I want to compute now is what happens at virialization. So what is virialization? What happens at virialization? And what is the density contrast, the density perturbation at virialization? That's what I want to compute in the next 10 minutes, OK? All right, so let's go. So first of all, imagine that you have a system of galaxies, say, or halos, whatever. And this system has some kinetic energy, total kinetic energy, and total potential energy. Right? And energy is conserved. And so energy conservation means that I call E, energy conservation is K, is the kinetic energy plus the potential energy. So just Newtonian physics, very simple stuff. And at turnaround, what happens at turnaround, so suppose you're considering now only this spherical perturbation. At turnaround, what happens is that the velocity stops, right? The expansion stops. So what is the kinetic energy of this perturbation at turnaround? 0. So at turnaround, the potential energy equals to the total energy. So this is the total energy, which is conserved. So that's what happens at turnaround. Now, if the system virializes, so what is virialization? Virialization is, again, a relation between the potential energy and the kinetic energy. And if the system is virialized, what happens is that 2 times the kinetic energy plus the potential energy is 0. So at virialization, the potential energy is, the potential energy is, is minus 2k, it's minus 2 times the kinetic energy. That's simple, right? So this is all that happens. This is the condition for virialization. So now I can use that the total energy, which is conserved, is phi. So if I plug this here, so this is total. If I plug this here, it means that the kinetic energy, so let me do this. The total energy is phi. So something's wrong. Sorry, there's something wrong here. Okay, just 1 second. So, sorry, this is the energy, sorry. This is the potential energy at turnaround, okay? And I want to compute what is the potential energy at virialization. So at virialization, this is minus 2 times the kinetic energy at virialization. And now what I want to show is the following. I want to show that, let's see now. So what I want to show is a relation between the energy potential at virialization and the total and the total energy again. So let me see. Sorry, there's something missing here that I thought was clear when I first read this. Okay. Right, so I have to compute the total energy, again, using virialized quantities. So the total energy, I know that is phi turnaround. Just a second. Sorry, this is, and this is, wait, why am I doing this? Something's wrong. Just a second. Yes. So let me do this. So total energy is, again, K potential energy plus kinetic energy. And this, I can use the fact that, sorry, there's something, sorry. I can use the fact that 2K plus phi equals 0 at virialization, so phi is minus 2K, and write this as minus K. So I just use that phi equals minus 2K. So this is minus K, but this is also 1/2 of phi at virialization. Sorry, so do you understand this? So, sorry, I was confusing. So what this means is that phi at virialization, something very simple, is twice the total energy as compared to phi at turnaround, which is the total energy. So what happens is that when the perturbation stops and starts to contract, the potential energy increases. And at virialization, it is twice as much as turnaround. That's all I want to say. So what this means is that its potential energy is inversely proportional to the distance of the radius of the perturbation. It means that the radius of the perturbation at virialization is 1/2 of turnaround, because the energy is twice as large. And that defines the radius of virialization for us. So remember that the radius of turnaround is 2a. So the radius of virialization is a. Is this quantity a. Okay? And therefore, this variable theta, where virialization happens, just look at the expression for r of theta. It's going to be 3 pi over 2. So again, what I'm assuming is that some process causes the virialization of this structure, and the contraction stops at this value here. So that's the physical thing that's happening. Yes.
Sorry, I don't remember. Why is it so clear that the radius follows that formula if the potential, like the potential is a half? Why is the radius?
Yes. So the potential energy in a gravitational field is proportional to 1 over r. So that's the reason. So the r, So if the potential energy increases by 2, it means that the radius decreases by 2. So that's the reason. Okay, so what I want to compute now is what is the density perturbation at virialization. That's something physical, right? That's what is happening physically. Infinities don't happen. So this is not happening physically. So what happens is that this thing will stabilize in a density which is the perturbation at virialization. And I want to compute what is this stabilization. So what I want to do is to compute for you what is the overdensity of structures at the time of collapse. So I'll explain this better. So T collapse. But keeping the density rho at the virialization value, at T virialization. So let me try to explain what I'm trying to compute here. I'm trying to compute something that is the following. So suppose here is time, okay? And you have a perturbation here, for instance. Let me call it rho, maybe, just something like that. So the maybe should I do with A or we should do with A? Let me do with the scale factor, which is better. So what happens is that if you start with some perturbation, remember how rho goes with the scale factor of a perturbation? How delta goes with the scale factor? Huh? Goes like 1 over A, right? Sorry. What I'm saying here. No, I'm sorry. So what I want to do is what happens with the density. So first I will plot the background density. So let me plot the background density, and the background density goes like a to the minus 3. So this is the background density. And now what happens with the perturbation? So the perturbation starts close to the background, if you remember. It's a small perturbation. And then it detaches from the background. And in principle, the density in perturbation, so this is, I should draw in another color. So it starts with the background. And then at collapse, it goes like this. But what I'm saying is that this should actually go like that because of virialization. And what I want to compute is actually this ratio here. I want to compute the ratio between the background density and the density in the perturbation at virialization, at the time of collapse. So this is T collapse, or A collapse. So is it clear what I want to do at least? So let me repeat. So we are looking at this universe, which is Einstein de Sitter. It has a density and a uniform density for the background. And I have a spherical perturbation. And the spherical perturbation, there's also a density inside. And this density in the spherical perturbation will increase with respect to the outside, with the background density. And this plot shows exactly that. Right? So this is the background density, goes like a to the minus 3. It's a matter-dominated universe. And this is the density inside the perturbation that in the beginning goes like the background, but then it detaches, and finally it explodes. But what I'm saying is that because of virialization, it does not explode. It stops. And I'm going to compute what is this ratio here between the background and the rho and the density at virialization. Yes?
There are two solutions for theta virialization, right? So pi over 2 and that value.
And what?
And that answer we got 3 pi.
Yes, yes.
And also pi over 2. And also gives the same radius. So why do we choose that one?
So pi over 2 is before that, right? So no, but we know that virialization happens when things are dense, and not when things are still this similar.
When it's contracted.
Yeah. Yeah. So physically, that's how it happens. Thank you. Okay, so that's what I want to do, and the way to do it, it's not difficult. So what I want to do is to compute a quantity, which is this ratio, which I call delta at virialization, which is rho at virialization, which means there's rho at theta equals 3 pi over 2, divided by the background density. And I will divide by the background density. So this is the background density. I put a bar, but I wanted collapse time, so theta collapse. So this is going to give me this ratio here between the density at virialization, because virialization happens at 3 pi over 2, with respect to the background density at collapse. Is that clear now? Okay. So, right. So it's not difficult to show. You have to substitute things, use the mass relations, etc. I not do it now. I leave it as an exercise. You can show that this thing, so the rho background is easy to compute. At theta collapse is 2 pi. And this thing you have to use the mass, the relation with the mass. Remember that the density is the mass divided by the volume. And the volume has the R that depends on theta. And the mass is conserved. So use that thing to derive what is rho at virialization. Use the background equations to determine this rho at theta of collapse. And you can find what this value is. I leave it as an exercise. If you have problems with that, you ask me, okay? So this number is the following. It's 18 pi square. This number keeps popping out, right? This type of numbers. 18 pi square. As simple as that. So what's 18 pi squared? It's like 178. So it means that when halos form, the density of the halos are typically like 100, 180, 200 times the background density. Now that number is kind of useful sometimes, especially when you try to find halos in the universe. Because it's not easy to find halos, okay? You see galaxies, right? When you take pictures, you see a bunch of galaxies. And in order to find halos, you should have algorithms that goes from galaxies to halos. And some algorithms uses this number to classify halos in your catalog of galaxies. So that's a number that comes out in halo finders, for instance, or when people talk about virialization radius, they also talk about this number. So this number pops up in many things when you are doing observational cosmology. So I just want to stress that this is a very simple model, but it has some realistic features. Okay, these numbers are useful, and this model is useful also. All right, any questions about this? Yes.
Is there a reason why they take the ratio of rho at the date of virialization, while the rho back on the date of collapse?
Yes, right. So yeah, you're right. So this is at the time when structures actually kind of form. So virialization happens a little bit before, but this ratio here does not change much afterwards. Right? This still decreases, but this is basically figure of merit. If you want to, if you tell me what is the density contrast of a halo at the time the halo was formed, this is 200 is the figure of merit. Okay, it doesn't change much. Yes, more questions? Yes.
As numbers for ITC.
Yes.
So for the CPM,
They
they usually use something similar.
use something similar. So usually, 180, 200. These numbers don't change much. Delta C, the critical density, does not change much. And these numbers also don't change much. What changes is the actual number of halos. That can change because we'll get into that. Very good. So I just want to finish this part of the spherical collapse model and just telling you something that I think it's nice. So the question I want to ask you, maybe, and give you the answer is the following, that you can think about. So I have a perturbation in this Einstein de Sitter universe that grows with time and eventually explodes, right? I didn't actually write an equation for the evolution of the perturbation. So the question is, can we write a differential equation for the evolution of perturbations, of these perturbations in the spherical collapse model, of the same sort of that Raoul wrote in his lectures, which was linear perturbation theory? And the answer is yes. Yes, you can. Yes, we can. So I just show you how to do it, and I show what the equation is. So you understand what the question is? The question is, can I write an equation for the evolution of the density perturbations in the spherical collapse model? So there's a nice, there's a way of doing it, which I think is nice. Let's see if I can find it. Yeah, I just show you the steps. You just need two things. So you just need two continuity equations. Remember, this is Einstein de Sitter, right? So there's only one fluid. And I write two continuity equations because they're two separate universes. Remember that we're talking about the separate universe approach? So there's one equation for what I call the background, and there's one equation for the perturbation. So I call the perturbation just, so the background I call a rho B. So this is the continuity equation for the background, where Hubble is A dot over A. And there's a similar equation for the perturbation, which I just put without a subscript. And there's a different expansion rate, which is R dot over R. Only with these two equations and taking time derivatives, etc., you can get an equation for delta. So again, delta is rho minus rho B background divided by rho background. The funny thing is that this is only a function of time now, right? Because these things are homogeneous. And you can find an equation for this. And the equation you find is the following. You can try to do this as an exercise. It's just maybe 2 pages and you'll do it. The equation you find is the following. So it's just time derivatives. That's the equation. Why did I write this equation? Because first of all, I can, which is nice to have an equation for the evolution of perturbation. Second thing you have to notice is that this equation is nonlinear, right? What Raoul derived was a linear perturbation equation. This is nonlinear. Where are the nonlinearities in this equation? So first there's a delta square, delta dot square here. There's 1 plus delta in the denominator. Here there's a delta square. So this equation is nonlinear, but this is the exact equation in this approximation, right? And if delta is small, you get back to Raoult's equation, as you should, linear perturbation theory. So this equation in the spherical, this you can derive in the spherical class model. It encompasses the time evolution of perturbations, and this one has divergences. This thing explodes. And you can find where it explodes, you can find delta C, you can do everything with this equation. So I think this is kind of nice. This equation, of course, has been derived in many places. Well, it has a assumption of Einstein de Sitter. I probably use it somewhere, but yeah. Right, I should probably use somewhere Einstein de Sitter in the derivation. I have the derivation here if you're interested. But anyways, I always find this nice, that you can derive a exact nonlinear equation for the evolution of perturbations. This in general you cannot do, right? So you can just do it here because of these assumptions of spherical symmetry. Okay, this concludes what I want to talk. I want to finish the spherical collapse model. And yes.
Why only appears here the expansion of the background?
Yeah, because I can use these two equations, take derivatives, eliminate this. You can do it. You have to trust me or do it yourself. Try to do it yourself.
What is a physical meaning of this?
Well, first of all, this is so the perturbation, the rho of perturbation appears here. The rate of expansion you could eliminate because of, you can take derivatives and just eliminate. which is good. So the only thing that appears is the rate of the background, not the evolution, not the expansion rate of the perturbation. And if it appeared, okay, you also have to be able to go back to the linear theory. If you have small perturbations, you can show that it goes back to the delta double dot plus 2h delta dot minus 4pg. So the equation that Rowe derived. So that's another, well, okay, there could be, okay. This is what comes out. This is the exact result. And you can do it. Trust me. Yeah. But this is nice. I like it.
This doesn't capture the virialization.
Sorry?
This doesn't capture the virialization. Divergence.
No, it doesn't. So this thing diverges.
Okay,
So virialization is put in by hand. So this is exactly the spherical collapse model without virialization. So virialization is not actually in the spherical collapse model. It's something I put in by hand, saying that, okay, there are some processes that are not captured in the spherical collapse model, so that actual divergences do not occur, right? You don't have regions of infinite density in the universe. Or maybe black holes are not even black holes, I don't know. Anyways, so I assumed that there was a virialization process inside the halo. And you see that in simulations. It's not that we're doing this blindly. You can see that in n-body simulations.
And just like even if just dark matter, the virialization here is something that's mechanical, right?
Yeah, it's just mechanics. It's just Newtonian physics. You're right. It's just Newtonian physics, dark matter in a box. That's the simulation I showed yesterday.
I was wondering why it's not there. Maybe they don't use the algorithm.
Oh, because, no. Virialization comes because you have several bodies interacting. Here, it's just a very idealized thing. It's just this perturbation that's growing, right? So it's very idealized. But it captures some features that we observe in more real simulations. Okay? More questions about spherical collapse model? Okay. So you can ask questions later. Now we're going to move to another topic, which is actually kind of related to the spherical collapse model, because the spherical collapse model tells us that, for instance, if I have a perturbation with a certain initial value here, let's say delta I, and this perturbation grows, eventually it will collapse. If this perturbation here starts growing, and if you can follow the linear evolution of this perturbation, and if the linear evolution of this perturbation goes to delta C, then you know that structure has formed. So we're going to use this in finding halos in the universe, and which is what I'm going to discuss now. So what I'm going to talk about now is a model to describe how many halos are formed in the universe. What is the density of halos as a function of mass? So you can form halos of different masses. And the question I want to address is if we can say something in a simple way, without doing simulations. Of course, you can always do simulations, right? But can we get some intuition on how halos form and how halos are distributed in the universe? What's the distribution of halos as a function of mass, for instance? So that's what I want to do now. So I want to discuss something called the halo mass function. So I didn't give in references for the spherical collapse model. There are several books that have this. For the halo mass function, there's a reference that I like a lot. You can follow it if you want. It's by Andrew Zentner. It's AstroPH. 06-11-454. So it's a review article about halo mass functions. So now we're going towards more observational things. So first, the idea is the following. So the idea that will permeate much of the discussion is that the perturbations are actually a random variable. So this delta of x, this perturbation that we talk about all the time, is a random variable. You can imagine that you have fluctuations. This comes from fluctuations, right? So you can imagine this as a random variable. So it's a random field. So I can make a drawing of this random field. I don't know, something like a random variable should do, right? Something like like that. So the thing is that something we have to discuss now, again, going more and more closer and closer to observations, is that we cannot observe, for each point in space. We have a telescope, we have a resolution. So we don't look at every point in space individually. We look at the region. So I want to introduce something we call the window function. That is something that has to do with observations. And so let me talk about the window function first. So this window function has to do with the resolution that you're observing, the telescope resolution. And so when you observe this in a given region of the sky, you will not see this, this very random behavior. You will see something that's smoothed. It's smoothed in a certain scale. So you see, for instance, see patches like this. And then you will compute the average and see something that's average in this patch here. So it's a smoothing procedure. That's what happens when you actually observe things. You have this observational window. So we are interested in these perturbations in the density field, or perturbation that are smoothed at some scale. At some scale that I will call for these lectures I call RW. So W is for window. So there's going to be a window, and I will define what a window is, a window function that will tell you what is the geometry that I'm observing things. And just to see if you can develop an intuition. Suppose I have the larger is this smoothing scale. What do you think is going to happen with the field in terms of fluctuations? It's going to be less fluctuating, right? So the larger the scale you're looking at, the less fluctuations the field will have, because you're smoothing at a larger and larger scales. Now, if you go to the universe and look at very, very large scales, the universe is homogeneous. If you look at small scales, the universe is completely homogeneous, right? So, so this gives you an intuition that the larger is the smoothing scale, the smoother is the universe that you're looking at, or the perturbations. Okay. So this window function, I will call it W, which depends on this, depends on position and depends on the scale, RW. And then we can talk about a smoothed density field, or which is what we actually observe. And that depends on the smoothing scale. And that's just a convolution of the window function which depends on the smoothing scale with your field. So when I say a smoothed field or a smoothed density field, that's what I mean. It's smoothed by a window function. And I give you some examples of window functions, okay, in a second. So of course, you can do this in Fourier space. And in Fourier space, a convolution is just a product. So if you do this in Fourier space, I can it's just this product. And we want this window function to be normalized. So we want the integral over equals 1. So is it clear the idea that we have this observational thing that's called the window function? Yes?
Why does the window function depend on the location?
Well, because you're pointing your telescope at some place, and at that place you have something that you can observe, and you cannot observe in other places, for instance. So it's going to be 0 in some places, non-zero in another place. You can think of different window functions. But it has to do where you point, no? So common choices for the window functions. Well, the most common choice is exactly this, that you have your telescope, you can see something in a certain region, and you cannot see anything in another region. That's the simplest thing, okay? And so you're smoothing that region. So common choices. Are what is called the uniform sphere of radius r, w. So that the window function is just this. It is 3 over 4 pi rw cubed for a point inside the sphere, and 0 for a point outside the sphere. So that's the simplest thing. So why it has to have this form? Funny form. It's a uniform thing, but why this funny thing? It's normalization, right? Just normalization. It has to be normalized to 1. Okay, that's the simplest possibility. But yeah. So it's very simple in configuration space, in real space. If you go to Fourier space, it's a mess. So sometimes you go to real space, to Fourier space here. You use the Fourier transform, but it's doable. No, the Fourier transform is, I have the expression here, just not even right, but you can do it. You can also do something that is less strict, so this is just something that has a sharp cutoff. You can think of something that has a smoother cutoff, like a Gaussian window function. You can do different things. I will not even write the other ones, but let's just concentrate on this window function. So just to tell you that there are others, okay? But so that's common choice, singular, not plural. So this is the choice I'm going to use. This is a top hat, yeah. So you can have a top hat. Another choice is a top hat in Fourier space, and then when you go to real space, it's complicated. And the nice thing of this is that you can define the mass inside this region, because this region is finite, right? So you can define a mass in this. This is going to be important. If you have another one like a Gaussian, you cannot define a mass, because in principle The Gaussian goes to infinity, and you cannot define the mass inside the perturbed region. So this is nice because you can define a mass inside the perturbed region. Anyways, so let's talk about, so suppose we can measure this smoothed density field, and I told you this is a random variable. So what is an important number that you want to know in a random variable? You want to know the variance of this random variable, right? So let's talk about the variance of this smoothed field. So the variance of delta x, the smoothed field, RW. So this is just sigma square, which is a function of RW. It's just this. Delta x RW, delta x prime RW. This is just, if you go to Fourier space, this is related to the power spectrum. But because we are going to Fourier space, so the window function, which is a convolution in configuration space, in real space is just a multiplication. So this is just going to be W squared of K or W. So this is the variance. This variance controls the probability of this smoothed field to reach a certain value, right? Because it controls the fluctuations of this field. So this is related to structure formation because what we saw in the spherical collapse model is that if the density perturbation crosses a certain critical value, you form structures, this delta C, delta critical. So this quantity, sigma square, controls the fluctuations of the smoothed field, right? And that's why it's important. So it will be important, will be relevant for structure formation. In particular, there is one important observational quantity that we use all the time, which is called sigma 8. So who here has heard of sigma 8? Good. It's a good thing, no, Raul, that people have heard of sigma 8?
I'm calculating it right now.
You're calculating right now sigma 8. So sigma 8 is one of the most important observational quantities. And guess what 8 is? Yeah, so 8 is this radius here, right? It's the 8 megaparsecs h minus 1. So sigma 8 is definition sigma of RW equals 8 h minus 1 megaparsec. So this is the variance of this primordial field fluctuations within a sphere of radius 8 megaparsecs, which is okay. So we usually think of this at redshift 0, okay? Projected redshift 0, linearly projected. And in fact, there's a, again, sigma 8 is related to these perturbations, the amplitude of these perturbations. Now, when Merdad talked about inflation, he also described something that has to do with amplitude of perturbations. What was the parameter that has to do with amplitudes of scalar perturbations? AS. So in fact, sigma 8 is not independent of AS. There's a relation between sigma, I can write down, but the transfer function, etc. And there's a relation between sigma 8 and AS. And some Boltzmann codes has an input, the amplitude of scalar perturbations, AS. Some have sigma 8. You can translate between them, okay? Just to let you know. So sigma 8 is something that's important. Yes?
Sorry if I missed this, but why 8?
Why 8? You have to define a certain physical scale. So this is totally
7 or 9
arbitrary. Yes, it's just sigma 8 was the choice because of historical reasons, and I don't know what the historical reasons are or where.
For the ICTP model, they thought it should be
Yeah. Yeah, you can compute that in some model. And actually, so CMB measures this, sigma A, which is not too different from 1. It's 0.7, 0.8, something like that.
That was when they thought the universe was not determinate. So they want a number that's include 1.
Yeah, and it's not very different from what we measure. Right. More questions? Yes.
Defining linear characteristic theory, or
It's defining linear perturbation theory, yes. So it depends on redshift, and the way it varies with redshift that we compute is based on linear perturbation theory. Yes. Okay. So now we are ready to talk about this model that describes how many halos are formed in the universe, which is called the Press-Schechter model. So another question, who here has heard of Press-Schechter model? Okay. Anna, you don't count. Yes. Sorry? Where? This here? Yeah. So this, yeah. So let me say standard deviation, right? Yeah, it should be squared. Okay, good. Variance is squared. Good, thank you.
But the experimental value that astronomers...
It's sigma 8.
C.
Yeah, they call sigma 8, yes. It's sigma 8, so, which is, of course, the square root of the variance. Now I want to talk about this very simplified model again. So I'm just doing simple things here. You know this, right? Everything is simple. and analytical, kind of analytical. So there's a simple model to find the amount of halos as a function of mass in the universe. And that's called the Press-Schechter model. Which is very old. This is from 1974. So this is very simple. I told you that you can interpret this density fluctuation, this density field as a random field. So we can write a probability distribution function for this random field. And the probability distribution function for this random field, so the probability of having a field the value delta at the scale, smoothing scale r, now I dropped the RW, sorry. Is that okay? Or should I keep the, maybe I should keep the RW. Here, the assumption in this model, so this is the probability of having fluctuations of delta within a range of delta and delta plus delta delta. Sorry about the delta delta, but that's what it is. And this is just a Gaussian thing. So that was the assumption of Press-Schechter in the original paper. It's a Gaussian distribution for the fluctuations. Now, if you were at the discussion section yesterday, I said this cannot be a Gaussian distribution, right? So there's a problem with this. It cannot be Gaussian. We know it cannot be Gaussian. That actually brings some problems. But for the moment, let's consider it's Gaussian, and that's easy. OK. So we also know that regions where this fluctuation is larger than the critical value that we computed in the spherical collapse model, will collapse into virialized halos. So the probability of a collapse in a given scale RW, is just given by the integral of this thing from what to what? From delta C to infinity. So any region that has delta larger than delta C will collapse. Right? So that's the idea. And also we can, sometimes I would say at the scale RW, sometimes I would say a certain mass scale. So the mass is related to RW. The mass is just 4/3 of pi RW cubed times the density. So we'll get there. Okay. So I call this, I don't know why I'm calling this, but so the probability for collapse in a given mass scale, m, which is given by RW. I write this as the following. I just follow some. So this is, I call f of m for some reason. So this is just what I said. Integral from the critical value to infinity. So anything that's above the critical density will collapse. So that's just the integral, an incomplete integral of the Gaussian distribution. This is sometimes it's called the error function. Okay, there are different names for this. But we can do this integral, okay? And the quantity that appears all the time is this ratio between delta and sigma square. So, right. So when you do this integral, this thing will be independent of delta, but it will be depending on delta C, on the critical delta. So one quantity that appears all the time is the ratio, as you would expect, between the critical perturbation divided by the sigma 8 quantity. If you do sigma 8. Or you can do sigma of m. So again, m is the mass scale related to the scale RW. And this quantity usually is given a name, which is nu. Right. And the typical mass scale happens when this guy is near 1. So when sigma of m star is near nu over delta C, where nu equals 1, sorry, is near delta C. Okay, so we can compute now the number density of halos in this model. So what I want to compute is the number density of virialized halos. With mass between a certain value m and m plus dm. So I call this number density of halos, that's the usual denomination, dn dm. So dn is the number density of halos, so it's halos per volume at a given range of mass m. So m is the mass of the halo, capital M is the mass of the halo, n is the number density, right? And this is just given by the number density, so rho over m. So rho is the density, and m is the mass. So rho over m is a number density. Do you see that rho over m is a number density? So this is just the number density times df dm, which is this probability here of having a mass m. So if you give me, so again, this is number density. This is number density. Yes. Thank you. Let's go back. Yes. And this is, so this is the so-called Press-Schechter model for the number density for a given mass. So this is this is what you get. All right. So you can plug in these integrals, ideally these integrals related to error function, etc. And what you get for the NDM is something like this: square root of 2 over pi. There's rho over m squared, delta c over sigma m. I can write this as in a better way. D log nu over d log m. And this is a modulus because this can be negative. So I guess this is why it appeared m squared here. And e nu e to the minus nu squared over 2. Where, again, this variable nu is just this thing here, which depends on m. So this is called a Press-Schechter mass function. Press-Schechter mass function. So again, this gives you the number of halos, number density of halos in a given mass range. So this is the distribution of halo density as a function of mass. Now the amazing thing about this is that it actually is not too far from what you, okay, Antonio maybe has a, some people say it's too far. It's not too far from what, as a first approximation, it's not too far from what you measure in simulations, for instance. In simulations, you have to find halos, of course. It's not easy to find halos, but the Press-Schechter mass function is not very different from what you find in observations. And this is the simplest possible so-called mass function. There are two or three observations I want to make. One is the following. So as maybe you notice, this is all based in linear perturbation, linear theory, because everything I computed is in linear theory. And this variable nu here, remember, nu is delta c over sigma m, right? So remember that this was found in Einstein de Sitter model. So if you go to another model, this critical density is going to be different. Usually it's not very different. It's a few percent, but it's in the exponent. So what I want to say is this, is that one way of checking different cosmologies that people have used and are still using is to look for the distribution of halos, the mass distribution of halos in the universe. So the mass distribution of halos in the universe is a powerful way of getting cosmological parameters. Right? It's not, so it has not been explored yet observationally, I think, to its full extent. So the dark energy survey, for instance, which I'm part of, we have a catalog of halos now, and we're in the process of doing cosmology with halos. So there are people in Brazil that are involved in this effort to get cosmology out of halo mass functions. Okay. The other thing that maybe you should notice is something that's interesting for Merdad, maybe, because this is something I never thought, but Matthias told me this, that if you look at this Press-Schechter mass function, you have something in the exponent that goes like 1 over the power spectrum. So it's non-perturbative in some sense, right? Because it's like when you do instanton calculations in field theory, you get the exponent of 1 over g squared, where g is the coupling constant. So this is something essentially non-perturbative. So maybe something interesting to do would be to understand how this thing matches onto perturbation theory. And this is something, okay, I thought about it, I never did anything. But this is something that could be interesting, okay? You cannot expand this for p of k equals 0, for instance, right? Not expand that. So how do you do this? I don't know how to do this, but this is just to tease Merdad and Raul about these things. So that's one observation that maybe probably was not clear to most of you, but yes.
I have a question about how sigma m is defined. Because
Yes.
talking before with sigma
Yes.
related to rate.
Yes. Thank you. Sorry?
I have a related question.
Yes.
If you choose
Yes.
a different window function,
Yes.
how you define the mass scale?
Right. So if you,
For instance, if you take a Gaussian.
yes, yeah, you have to cut your Gaussian at some point.
So the mass scale is a parameter.
Yeah. Here is a parameter. Yes, absolutely, it's a parameter. Yeah. Thank you. Yes. So that's one. The second observation is that this is the simplest model for the halo mass function, and there are several different models in the literature that goes by the name of Shaft-Thorman mass functions, of Tinker mass functions. There are several different mass functions, and they're usually a form not very different from this, but with more free parameters that are fitted in simulations. Like Tinker mass function is fitted on lambda CDM simulations. Okay, but the motivation for this parameterization of mass function comes from Press-Schechter. So Press-Schechter is a basis for mass functions if you think about it. Yeah. All right. So that's one thing. And the other thing I should mention is the following: is that we're talking about halos here, but usually sometimes when you are talking about perturbation theory or things like that, you're usually talking about the dark matter or matter perturbations, not halo perturbations, right? So there is a way to relate fluctuations in halos, so perturbations in halos. So the halo density can fluctuate from here to there. And there is a way to relate fluctuations in halos to fluctuations in the matter. And the way to do this is to use something we call bias. So who here has heard about bias? So many people. Anna, you don't count. You didn't raise your hand, but And there are two types of biases, okay? I talk about halo bias, so this is the bias between halo fluctuations and matter fluctuations. And something also that you hear later on, next week, is galaxy bias. So that's the difference between perturbations in number of galaxies and perturbation in matter. Those are two different things, so don't get confused, okay? There's halo bias, there's galaxy bias. And here, when you talk about halos and you want to compare with the matter fluctuations, you have to introduce a parameter or more than one parameter called the halo bias. So the halo bias is a relation between the fluctuations in halos and fluctuations in matter. And the galaxy bias is something similar in definition, but just with galaxies instead of halos. So the halo bias you can define as, I call perturbations in halos. Delta H is perturbation in halos now. You can define this as just some expansion, BI, which can depend on the halo mass, for instance, times delta of matter to a power I. So this is power I, so delta to the power 0, delta to the power 1, delta to the power 2, etc. So this starts at 1, actually. So the simplest approximation is just to have a linear relation, which is called linear bias. If you have only the first term, it's a linear relation between the halo bias, the halo density and the matter density perturbation. But you can have quadratic bias, etc. Okay, it's possible. All right. So people usually stop at the linear halo bias. And there's something similar to galaxies, and this is, maybe I should put an age here just to say that this is halo bias. So this model is very useful to model. So this model is very useful to study the distributions of halos as a function of mass. And finally, to finish up, really? Okay, so in 10 minutes, I talk about another very useful model, which is called the halo model. So this lecture is all about halos, right? Lots of halos here. Okay. So in 10 minutes, halo model. And the halo model is, again, a non-perturbative model for perturbations in the universe, which is analytical. I mean, you can do things without simulations. So halo model. And if I can choose a reference for the halo model, I suggest this paper of Correa and Schaff. It's 2002. I don't have the archive number with me, sorry. So the halo model is a model for the distribution of mass in the universe. So it goes beyond perturbation theory. It's a non-perturbative model, fully nonlinear model. And it has one basic assumption. And the basic assumption is that all the matter in the universe is distributed in halos. That's the only assumption. So all the matter that you see in the universe are in halos. So in order to describe a halo model, we need a few ingredients. So we need to know how matter is distributed in one halo. So the easiest thing, the simplest thing, we think, okay, matter is distributed uniformly in halos, right? That would be the simplest thing. That's not what is observed. So there's more matter towards the center of the halo, for instance. So there's something that we call how the density changes inside the halo. So imagine you have a halo, you have matter, and you have density in the halo, right? The density is not constant. It actually increases at the center. And the way to describe how matter is distributed in the halo, we need to know this, what is called a density profile, how the density changes as a function of the distance to the center of the halo. That's called a density profile. So that's one of the ingredients that we will need for this model. The other ingredient that we need to know is how many halos are there. So we just saw that. That's the halo mass function. That's another ingredient. Okay. So, all right. So the ingredients are, for a halo model, is the halo mass function that we just talked about. The halo density profile, so how matter is distributed inside one halo. So this is how halos are distributed in the universe. This is how mass is distributed in one halo. And in principle, we also need the halo bias to relate halos to matter. Okay? So the idea is the following. Suppose I want to find correlation. So we're talking about, say, two-point correlation functions, right? Power spectrum, two-point correlation functions. So you need to know the correlation between points in the universe. So in a halo model, if you want to look at two-point correlation functions, there are two possibilities for these 2 points. What are these two possibilities? Okay, I repeat the question. Close your eyes, don't sleep, and think of the universe as being composed of halos. And then you want to compute correlation functions in this universe. 2 points. So there are two possibilities for these 2 points. One possibility is that these 2 points are in the same halo. So those are scales of the size of a halo. And the other possibility is that they're 2 different halos. Those are the 2 possibilities, right? And in fact, when you compute the power spectrum or the correlation function in a halo model, you usually have contributions from something we call the one halo term, when the 2 points are in one halo, and contributions from the two halo term, when the 2 points are in 2 different halos. So that's for 2-point functions. You can generalize this for n-point functions, okay? And then you have many different possibilities. Okay, so maybe I should just skip everything and just show you. Right. Yeah, you can do lots of stuff with this. I don't have the time. So if you ask me questions, I didn't do anything about the halo model. I don't have the time. So I just tell you that usually, for instance, so one of the main results of the halo model is that given these ingredients, you can compute a power spectrum, 3D power spectrum from the halo model. And this will have contributions from one halo term, when the 2 points are in the same halo, and contributions from 2 halo terms. And in order to compute this, for the one halo term, for instance, the only thing that's important is the halo density profile, and not how halos are distributed in the universe, because you're only looking at things that happen in one halo. And 2 halo terms, it's important to know the halo mass function as well as the halo density profile, and also the halo bias, if you want to talk about galaxy distributions. So the halo model is a whole. Now, it would take another half an hour. I don't want to go over time. I just want to tell you that the halo model is, again, a very useful way to go beyond linear perturbation theory. Okay? So people use the halo model to find the power spectrum for, suppose you are doing lambda CDM, and you want to compute the power spectrum. Then you can run simulations. They're very accurate simulations now. And you can compute the power spectrum non-linearly. There's no problem with that. There are many simulations. Even if you change parameters in the lambda CDM model, there are a suite of numerical simulations that allows you to interpolate, this is called emulators, that allows you to interpolate results for different cosmological parameters in lambda CDM, let's say. But now suppose you want to test another model, say modify gravity or something like that, and you don't have enough simulations to do this. Okay? So what theorists usually do is to use the halo model for that. Okay? So it's an important tool, it's a useful tool to test your theories, even beyond lambda CDM theories, in the nonlinear regime. And that's really the important part now in the cosmological analysis of large-scale surveys, is to fully take advantage of data in the nonlinear regime. So you can measure things in the nonlinear regime. That's no problem. The problem is the modeling and how to model physics in the nonlinear regimes and take advantage of data in that regime to constrain parameters of your model or parameters of beyond lambda CDM models. So in this sense, the halo model is really important. It's even being used, for instance, to study the importance of baryons in modeling your data. At small scales, baryons are important, and there are modifications of the halo model that are sufficient flexible to account for baryons, which is something very difficult to do, right? Simulations involving baryons are really hard, really costly, and people try to use halo models to describe, at least not in detail, but describe the effects of baryons at nonlinear scales. So halo model is one important. I didn't do justice. The reason I'm telling all of this is that I didn't make justice to spend 5 minutes talking about the halo model, because it's a large body of knowledge that it's being more and more useful. So what we're going to see next week with Marko Simonovic is a continuation of this course, but he's probably going to talk more about the regime that is not fully nonlinear, but is what's called mildly nonlinear, using techniques that goes a little bit beyond the usual perturbation theory. So I think next week have an excellent course that will continue some of this stuff. So thank you very much. Questions?
When you assume all matter is in halos,
Sorry.
all matter is in halos.
Yes.
How good is this assumption?
Well, yeah, so how good this assumption is. So we see that the galaxies are usually in clusters of galaxies or halos of galaxies. In simulations, we see everything is in halos. So there's some voids, and yes. So
when even a void is a halo, then everything is in a halo.
Yeah, so that's right. So I guess the right answer to your question is how well this describes the universe. So they have to use the halo model, compute the power spectrum, and see how it compares with the power spectrum that you measure. And the comparison is not too bad, okay? So it really reproduces the features of what you expect. So in that sense, it's a good assumption. I can get to your mic.
And there are also theories like effective field theory approaches to things like bias on the nonlinear regime. And the halo model has, it's not perfect, right? So people are looking for small effects on this nonlinear scale. So what do you think about this? Maybe when you have to choose between these approaches, what you think? What are the benefits of halo model approach and the effective field theory approach?
So we're going to hear a lot about effective field theories next week. So that's Marco's specialty. And so the question to ask Marco is how far in the nonlinear regime he can go. Or maybe you can ask Merdad. And it goes to this what's called mildly nonlinear scales, but cannot go to full nonlinear scales. So you can ask this to Marco next week. Yes.
Rogerio, so you mentioned that in DES you guys are working on a halo catalog. Is that what you said?
It's a cluster catalog.
So it's coming from clusters and then measuring the mass using strong lensing or
weak lensing.
Weak lensing?
Yeah.
Okay. I was just curious about.
Yeah. So there's a paper that should be coming out using. It's still the year one cosmology, so year one data. The reason why it has been taking so long, so one question that you should ask is how do you measure, so I talked about cluster mass, right? The halo mass functions. So the question you can ask is how do you actually measure a mass? And the reason, and the answer is difficult, very difficult to measure mass. And one way that DS is doing it is to have a relationship between, so you calibrate a relation between the mass that you can measure for some clusters using weak gravitational lensing, which weak gravitational lensing measures the mass because of the gravitational deflection of light, and calibrate this with the number of galaxies in a cluster, which is called richness. So there's something called richness-mass relation. And the calibration of this is complicated, but is being done in DS. And this is what is an input in order to get, say, mass functions and things like that and compare with models.
So the errors are going to be small enough that you can distinguish between different, because with weak lensing, the errors are always pretty large.
Yeah. So I've seen the plot of the mass richness calibration. And the progress they made is amazing. I was amazed. So in that plot, in the mass richness calibration, this calibration is much more precise than it used to be. Now, the analysis is taking more time because it's more complicated. It's not only that, right? So there's more complications. So hopefully it'll be out at some point. It's not out yet, is it, Felipe? The cluster and I'm being recorded, so I won't say anything else.
So in a survey, do you have, you're working with galaxies and you want to measure like a mass function. Should you switch from mass to magnitude or something like that? Because I imagine this.
Sorry, say it again?
So should you work with magnitude instead of mass? Because I imagine for each individual each individual galaxy, it might be hard to get a mass estimate.
Right. So you're telling me that maybe the magnitude of a galaxy can be a proxy for the mass of the galaxy? I don't know. I haven't seen this done. Maybe Raul knows.
You mean in the context of the halo model, things like this?
Here, yeah.
For example, in the Press-Schechter mass function.
Yeah. So, or in the mass function. Well, the problem with you could use perhaps the mass of the largest galaxy in a cluster, something like this. And this, I think, people sometimes do something like this. You know, the brightest galaxy. It is a useful way. Many people do calibration of clusters using the brightest galaxy in a cluster. But for the Press-Schechter mass function, this is really a matter of the whole matter in the universe. So you need this is a statement about how much mass you have and how it ends up in systems of larger and larger mass, total mass. So that includes dark matter. So just taking the mass of the galaxy to that formula doesn't work. However, as a proxy, yes, it is used actually.
Yeah, actually, another thing that's used is X-rays. So X-rays measures the temperature of the gas, and that has to do with the thermal energy. That has to do with the mass, total mass of the cluster. So that's being used also to calibrate cluster masses.
I'm a little bit confused what a halo bias actually is, because what I know from galaxy, we try to probe the density profile through using galaxy luminous matter, we have the bias which is this departure from the density profile, but I do not see what exactly is that delta M there, and what is halo bias.
Yeah. So this thing here is the fluctuations of the number of halos. So you can have more halos in one region than in another region. And this is the fluctuation in matter density. So you can have more matter density in one region and less matter density in another region.
But luminosity matter or?
This is matter. So this is
Total
all matter.
Okay.
It's not only luminous matter. So what you're probably thinking about is the relation between the galaxies, which is luminous matter, and the total matter, which is matter plus dark matter. And the relation between these two, which you also can do an expansion like this. This is called the galaxy bias. So that what relates luminous matter, so what you observe, galaxies, with the matter, total matter.
So what is the difference between this total matter and matter in a halo? I didn't get that.
So again, it's different because you can have halos, and halos can have their own statistics, right? You have fluctuations that are different from the matter fluctuations. Maybe Raul can.
Maybe you can draw a picture. Like, matter is all over the place here. Halo, you count halos here, there, there. So delta n over n is the number counts, right? Number 1, 2, 3.
Yeah.
And count divided by the mean. That's what you call delta of the halos.
Yes.
Something like this. Whereas if you say matter, that's really rho, delta rho over rho, and that's a continuous field. So you average the continuous field over here, compare with that count. Those are two different things. Halos have different masses. Big halo.
Yeah.
Suppose here you have a big halo with a huge mass. This is a small halo with a small mass. Each one of them has a different bias.
Yeah, the bias can depend on the mass.
So a very dense region ends up with, dense region ends up with a few very large, very massive halos and has very high bias. And conversely, regions of low density have low mass halos.
And remember that halos only form in regions which have density fluctuations larger than the critical value. So it's like you're getting the peaks of the fluctuations in matter, and those peaks form halos. But there are smaller fluctuations in matter that does not form halos.
My picture wasn't really good, though.
That's good. So before you leave, don't forget at 5 o'clock, there is a special seminar by Mehrdad on the spin of primordial black holes. Okay?
By the way, and I should make an announcement. In the exercise, in the problem set that I gave you on Wednesday, the second problem there, I made a slight confusion. You remember that we found that the density contrast in the linear regime goes like in the matter-dominated area, like A of t, right? So this is basically some initial value times A. So sometimes we call this here, we say that we define this as some function d times in a general situation and delta I here, right? So there's an equation for this thing here, which is a deviation from what we call an ICTP-Trieste matter of the universe. And the equation I gave you there was for this, and not for what you have here instead of A of t here, right? So basically, see, G is equal to A of t in a matter-dominated universe, but in a dark matter-dominated universe, we define this G. And there's a factor of A there, which I forgot to tell you that there was a factor of A. So the equation was completely wrong. Actually, it was my student Francisco that told me, it's like, how does the equation doesn't check? It's true, because I copied the wrong equation. I gave you the wrong variable. So instead of G is, the equation should really be for this big time. So I already corrected this on the problem set, so you can already take a look. Sorry about that.
Okay.
Now it's on. Sorry.
So let's have coffee then.